Okay, I hope it was clear that the previous solution we saw here was done with a linear heating that's dependent on SST, and you could see the result here. And now we go to a nonlinear heating example to show that you can get the multi-structure behavior of MJOs when you do nonlinear heating under frictional convergence instability. Again, this is model dependent. Also, in case it wasn't clear, this was the heating coefficient due to wave convergence, which doesn't by itself give the multi-scale structure. What do we mean by a multi-scale structure? Essentially, that is the convective complex, which is essentially at planetary scale, and within that you have these MJO convection, which is very local with its supercloud complex supercloud clusters propagating eastward, tilting backward, and then you have the two-day waves which are propagating westward and tilting forward, and they are situated behind the MJO structure for the SEC supercloud cluster, and in front of the MJO for the two-day waves. We will see that in the next podcast. So the heating coefficient due to frictional convergence is what we are looking at, basically arguing that by themselves neither the wave convergence or the wave cisc and nor the heating associated with the evaporation can give us this multiple structures. There is a multi-scale model as well that we will look at in the next podcast. Looking for a solution that is then got a nonlinear heating, which is positive only and SST dependent. So when precipitation happens, there is a heating, but there is no cooling, and SST is dependent on the longitude as well as season, as we will see in the animation in the next slide. That gives us nonlinear heating, and this is related to observed relation between convection and SST. So it's not just made up, but it's based on empirical evidence. And you look for the multi-scale solution that comes out of this. So you're looking at sequential maps of the precipitation rate in solid contours and the lower troposphere geopotential perturbation in dashed contours. So be careful, the solid contours are there and the dashed contours are there. So everywhere there are small scale solid contours because precipitation tends to be small scale, and then you have the planetary scale geopotential perturbations, and all three fields are normalized by the respective maxima at in each panel. The contours start from point 1 and interval of point 2. The main point is we are looking here at day 0, 4, 8, 16, 20, 24, and 28 after the model is initialized with a Kelvin wave in the free troposphere, and the large-scale structure is accomplished basically by convective heating driving the large-scale perturbation of the dry Kelvin and Rossby waves. So the Kelvin wave travels eastward at almost 50 meters per second, gets ahead much further very quickly, and you can see the convergence that is being driven into the convective center. So you have easterlies ahead, as we have seen before, and the Rossby waves, dry Rossby waves, propagate westward, and they move much more slowly, of course. You can look up the speed, should be about 1/3 in a state where there is no background flow. Doppler shifting of the waves in the atmosphere, especially Rossby waves, is very common. So all these kind of solutions are often done with the background state being stationary, which simplifies the process understanding. Okay, so day 0 already Kelvin wave is out ahead. By day 8 you can see it's more than 1,000 kilometers, and the slow propagation of the convective convection centers, smaller scale convection centers, is slowed down much slower than the dry Kelvin and Rossby waves because of the frictional effects that we already mentioned. And the dry Kelvin wave goes around the planet and comes back, and the frictional convergence here is argued to explain also the longitudinal dependence of the propagation speeds of the MJOs. Well, that is one explanation in this model, in this particular chapter. So if you look at the seasonal cycle, this is actually showing multiple years, so you have to just watch the time here. But you know that as the sun moves north, the entire warm pool, for example, here moves north with the sun, so you can see that clearly, the entire system moving back and forth. And during the fall winter months of the boreal seasons, there is a little bit more symmetry around the equator, which favors the MJO propagation as well. But the longitudinal contrasts of sea surface temperatures also affect the MJO propagation speed, especially when you go away from the warm temperatures around the dateline into the colder temperatures in the eastern Pacific. The convection is going to die away because the temperature SSTs drop below the convective threshold. The heating is gone, but the dynamic structure in terms of the convergences and divergences in the wind field, for example, continue. They cross over the South American continent into the Atlantic and often are reorganized once they reach the warm temperatures in the western Indian Ocean. So there are what are called primary MJOs and secondary MJOs that are related to whether they are regenerated from the previous MJO, remnant of a previous MJO, or if they are born fresh based on perturbations from the extratropics. There are various mechanisms proposed for generating MJOs as well, but I'm getting a bit ahead. The main point to see here is that the frictional convergence in this model and the related heating are argued to explain the multiple structures in the MJO, the convective complex, which has the planetary scale with the dry Kelvin waves and the dry Rossby waves, which move at the almost the free wave speeds around the globe, but the convectively coupled Kelvin and Rossby waves move at the speed that we expect for observed for MJOs, which are much slower than the free waves. And it can explain the longitudinal contrast of the MJO propagation speeds. Okay, so that's the nonlinear heating and frictional convergence instability with the nonlinear heating, which in this case is prescribed as a positive only dependence on SST and precipitation. Okay, so still simplified models, but very important for understanding some of the properties of MJOs. We'll then come to the multi-scale structure and the associated model in the next podcast, where you have eddy momentum transports happening with the super cloud clusters in the westerly part of the MJOs and the 2-day waves in the easterly part of the MJOs. Okay.